We're going to start chapter 5 today, which is the last of the review chapters. Again, the first 5 chapters in this book are a review of what we've already done, the general chemistry. And when we're done with this chapter, then you'll have your first unit test. It'll be over the first 5 chapters, okay? So today we start chapter 5. And chapter 5 is about changes of state, in other words, changing from a solid to a liquid to a gas, and so on, and the gas laws, all right? So when we talk about changes in state, we're talking about changing from one physical state to another. No chemical reaction going on here. And what happens is you change the energy of the particles. Okay, so if you have a solid, you know, those particles aren't moving the atoms and the molecules, that's what I'm talking about when I say particles. So they're not moving very much. They're just kind of hanging together tight. You add some energy to them and they start to separate. They start to move apart a little bit. And as you move apart, then they become a liquid. Okay, if you add more and more energy, then they really start moving apart and then you got yourself a gas. So a change in state is a physical change because the covalent bonds aren't being, you're not changing the atoms and the molecules. What you're doing is you're messing with the forces in between the molecules and atoms. Remember, we always talked about intermolecular forces. There's a force in between them, and you're changing those. Okay, if you're adding energy, you're breaking those bonds or you're moving those apart, but you're not messing actual with the atom and the molecule. They're the same. Okay, so the inter in the molecule, those forces, the inside the molecule change, the inter in between the molecules, that's the ones that changes, okay? The London dispersion forces, the dipole forces, the hydrogen bonding forces, those are the ones that change, okay? So in a gas, there actually isn't even any intermolecular forces. Those guys move so far apart, the particles aren't even close to each other, so there's no forces that occur there. So when you're talking about forces in between molecules, that only happens in solids and liquids. Doesn't happen in gases, okay? So the intermolecular forces exist in the liquid, and they're really strong in the solid, okay? That's where you get the forces. And again, this is not in the molecule itself, but in between the molecules. Because remember, in 1 mole, if you have 18 grams of water, that would be like a half glass of water, a small glass of water. You have 6.02 times 10 to the 23rd molecules. That's a lot of molecules in a small space. So they're going to have forces. They're going to be attracted to each other, okay? So when you want to change state, okay? So when you change state from a solid to a liquid, you melt it, okay? If you reverse, if you go from a liquid to a solid, that's freezing. And the point at which they occur is the same. Now, if you're talking about water, that's easy. That's at 0 Celsius or 32 Fahrenheit, okay? When they change from a liquid to a gas, it's called vaporization or evaporation, okay? That's when it goes from a liquid to gas. If you do the reverse, that's condensation, okay? And condensation would be like in the spring when you come out and your windshield is all wet. You have this gas vapor in the air and it hits your cool windshield and then it becomes a liquid. So then you got water. In the winter, it's not great because that happens and then it freezes and then you got to scrape your windows, okay? A solid, there's a few. Now, this doesn't happen for all elements, but a solid can go directly from a gas to a solid, and that's called sublimation, okay? Sorry, I said that backwards. A solid to a gas. I did deposition first. A solid to a gas would be an example would be like carbon dioxide. You guys ever put carbon dioxide in your punch bowl at Halloween so you get the smoky effect? Okay, carbon dioxide goes from a solid to a gas. It does not become a liquid in between. There's a few other elements. Iodine's another one that does that. It goes from a solid to a gas, but there's not very many. And then there's some that go from a gas to a solid, and that's called deposition. Okay, and that happens with some of the atmospheric gases, things like that. But again, these aren't very common. They're much less common than your standard evaporation and condensation and things like that. Okay, so if you're going to melt or you're going to go from vaporization, sublimation, what happens now is the intermolecular forces are disrupted because of kinetic energy increases. So when you have a solid and it becomes a liquid, you're going to add some energy to it. And because you have more kinetic energy, the particles are moving faster. So they're going to start, messing with those intermolecular forces. And that's why they can spread out a little bit. Okay. The opposite, condensation, freezing, and deposition. Now what happens is you're going to take away energy. You're going to take away some of that kinetic energy. And so the particles aren't going to move as fast, so they get closer together. So if you think about it, when you go from a liquid to a solid, the particles have to be closer together. So you're going to take away some of that kinetic energy so the particles don't move as fast, and then they hang out closer together because you have those intermolecular forces. They're stronger then, okay? So energy has to be added to melt, to go through vaporization or sublimation, okay? So if you want to do any of these forces, you have to add energy. If you're doing the opposite, excuse me, like you're going to freeze something, or it's going to go from condensation, which means it goes from a gas to a liquid, or deposition, any one of those, then you have to take energy away because you don't want the particles moving as fast, so you take them away. Okay. Again, with changes of state, evaporative cooling is the removal of heat from a surrounding area. We do this when we sweat. When you sweat, the reason why you cool off is when the water evaporates, the sweat evaporates, it takes heat with it, and then you cool off. Condensation requires that heat be removed from the gas phase. And again, if you've got gas vapor in the air and it hits a cool substance like your windshield, okay, now instead of being a gas now it becomes a liquid. You took away some of the energy from it. Now the particles are closer together, so it changes from a gas to a liquid. Okay, so when energy is added to a solid phase, you're going to increase the kinetic energy. Because the particles are moving faster, then you don't have as many intermolecular forces. They're not as close to each other, so the forces start to break, and that's why things melt. When energy is added to the liquid phase, okay, so now you wanted to change from a liquid to a gas, okay, again, you're even added more energy, so the particles move even farther apart, so there's even less intermolecular forces, because intermolecular forces are strongest in the solid, then the liquid, and they don't even exist in a gas. Okay, they're just too far apart to even, they don't interact at all. Okay, so you can show this in what they call a heating curve. Okay, it shows how the temperature, the crazy thing about it is if you took ice and you started to melt it, you put it on a hot plate and you started melt it and you monitored the temperature. What you would notice as the ice is, what's changing from a solid to a liquid, during that time, the temperature does not change. During a phase change, all the energy you're adding is going to breaking those intermolecular bonds and changing it from one phase to another. Okay, once you got all the ice melted, now the temperature is going to rise. And when it rises, it's going to go, the temperature is going to go up greatly. And if you're talking about water, it's going to go from 0 to 100. Then when it gets to 100, then it's going to be flat again because now you got to change that gas or all that liquid to a gas. So anytime you have a phase change, there is no change in temperature. Okay? And I have a graph to show you that in a minute. But whenever you see on a heating curve, anytime you see a flat spot, you know that's where a phase change is occurring. Okay? Right here. Okay, this explains it better. Okay, so I have some ice and I'm going to melt it and change it to a liquid, and then I'm going to boil it off. All right, so I start out here and it's below 0. Okay, and it's going to heat. I'm adding heat and it's getting up to here. Now, once it gets to 0, that's where ice melts. So you notice, even though I'm adding heat, the temperature is not increasing. During this time, this is a phase change. This is melting. Okay, now I get to this point. At this point right here, all the ice is gone. Now I just have a liquid. So again, heat it until this point. Okay, so it's all a liquid, and I'm just getting it hotter and hotter and hotter. When it gets to this point, now it's going to start to boil. And this is vaporization. This is when all that liquid changes to a gas. And again, notice flat spot. And actually, this is a little off because the melting is usually a much shorter phase change than vaporization. It takes a lot more energy to change it from a liquid to a gas than it does to melt, to change it from a solid to a liquid. But again, anytime you see a heating curve, if you see flat spots, that's a phase change. Okay, so the changes in phase, when you're changing them, you're going to melt them and boil them or whatever. They're going to have different characteristics, different physical characteristics at those points. Okay, if it's a non-polar covalent compound, this would be like oils, soap, some of the organic compounds, they have a lower melting and boiling point because their intermolecular forces aren't very strong. Okay, in a non-polar substance, remember, you don't have dipoles, you don't have hydrogen bonding, all you have is dispersion forces, and dispersion forces aren't very strong. So if I take a non-polar covalent compound, it's really easy to melt it. Okay, One of the things that we do in a lab if we were here is we'd melt PDB, which is mothballs. Perodichlorobenzene is its fancy name. It's an organic compound, and it will melt in probably 15 seconds. It'll change from a solid to a liquid. Just as soon as you put it on the hot plate, it starts to melt because it has, it's a nonpolar. It doesn't have very strong intermolecular forces, so it's easy for it to melt. Okay. If you have hydrogen bonding compounds, they have much higher melting and boiling points. Like water, you got to heat it up to 100. Okay. So there's a difference if the bonding type is going to determine what type of intermolecular forces they have as well. And then if you don't have very many, if you only have weak ones like dispersion forces, they melt really easy. But if they have hydrogen bonding, dipoles, that kind of stuff, then you have to add a lot more energy in order to get them to melt. Okay. Okay. So when you do that, there's actually a measurement. Okay. The amount of energy required to melt a solid is called its heat of fusion. Okay. And it's enthalpy. They do it like this. Delta H means a change in energy, and FUS means fusion. So this is a point at which it melts. And for water, it's 6.01, I think. Okay. Okay. If you do the opposite, not the opposite, but if you move up on the scale, the amount of energy required to vaporize a liquid at boiling point, the heat of vaporization, again, change in H is VAP for vaporization. Now, if you want to compare, like I said, it takes more energy to do this. For melting for water, the heat of fusion is 6.01. The heat of fusion for vaporization for boiling water is 40.67. So it's, 7 times as much. So there's a lot more energy required for vaporization than there's for fusion, and that makes sense. Okay. So a cooling curve would be just the opposite of the one I showed you where we had it going up. Now we're going to have one going down. Okay. When we talk about, but we'd have to start at steam, and you'd have to worry about that because again, the heat of vaporization is a high number. There's a lot of energy, and it would be transferred to your skin, and that's why, ouch. Have you ever done that when you take something out of the microwave that you heat and you open up the bag and it, burns your fingers? You gotta be careful. Steam has a lot of energy, so you gotta be careful. Okay, so when you're changing your state, there's something called vapor pressure. There's pressure that a gas exerts on, sorry, I was just looking at the time. I don't want to run out. I do that sometimes, and I apologize for that, you guys. Sometimes I'll be just talking and cut off. But anyway, when we're talking about changes of state, now when we start talking about gases and liquids too, you have, like, let's say you're going to make pop. Okay, you want to take your carbon dioxide pop and you want to put it in that liquid, whatever whatever pop you're making. You have to overcome that pressure that's at the surface of that pop. Okay, and when you're looking at pressure, it's force over area. Okay, so pressure is the force per unit area and is exerted by gas particles when they hit the wall of the container. That's why when you have a bottle of pop or a can of pop, it's pressurized. You keep that top on, and as soon as you release that top, you get that. That's called effervescence, you guys. But anyway, you get that release of pressure because you were forcing it in there. You were holding it in there. And once you release that pressure, out it goes. Okay. So when you're talking about liquids, if they have a high vapor pressure, that means that they will release their particles easily. They become a gas real easily. And it's really easy to tell. It's called volatile. It's really easy to tell if it has a smell. Okay. Gasoline is one of the most volatile substances. Gasoline will change from a liquid. I mean, when you're pumping it, you can smell it, right? It changes to a gas easily. It's very volatile. Okay. If they have a smell when they're liquid, and when you're doing chemistry, you guys, you don't go at things, you waft. If you can't remember that, like if you have a test tube, you don't snort the test tube, you waft it. But if it has a smell, it's volatile. Okay. Vapor pressure of a substance increases with temperature. So the hotter the temperature, the more it'll change into, the vapor pressure will increase. So if you have a normal boiling point of a liquid, the temperature at which the normal temperature at which it changes is 1 atmosphere. Okay. If we boil water in the lab in Belcourt, it's not going to boil at 100. It's actually going to boil a little lower than that because we're not at 1 atmosphere. Okay. We're different than sea level. So there's going to be changes. Okay. Because there's not as much pressure. Okay. So whenever you're talking about molecules in the air, they actually exert downward force, pressure, because of gravity. Gravity pulls them down just like a